In this video, we will discuss a few more examples of the applications of fundamental theorem of calculus of part 2. So this is one of the key findings of calculus, or even all of the math. This is one of the key results. Well, let's start from recall what is the second part of fundamental theorem of calculus, right? So this is the fundamental theorem of calculus. So one of the key results in calculus, not even in calculus, in all maths. Part 2, right? Our assumption is our function f is continuous on AB, right? And if this function is continuous, then this is what's that integrable, right? So what's the meaning of that? It is integration from a to b f of x dx exists as a finite number. We are looking for a different way to find that limit, because integral is defined as a special limit, which if you want to evaluate that limit, it's very hard in majority of the cases. So this fundamental theorem of calculus nicely makes connection between integral and antiderivative, right? So the result here is then what happens is integration from a to b f of x dx equal to f x, then plug in a, plug in b, then you get this do a subtraction, right? You get this is same as f of b minus f of a. So that's a easier way to write down a difference of two numbers. And what's capital F? Just as we introduce the antiderivatives. So capital F is any, right? There we discussed there are infinite many antiderivatives. This is one of them of F on AB, right? This is a direct implication of fundamental theorem of calculus part 1. So you can derive this result directly from the part 1 of fundamental theorem of calculus. So let's just use FTC2 to represent this is the second part of the major result, right? So to figure out the definite integral, so this is definite integral. All you need to do is figure out antiderivative and then plug in the upper bound, lower bound, do a subtraction, right? Let's see examples. Let's see two examples in this video. Example 1 here is we have integration from 0 to 4 and 4 minus t root t dt, right? So we don't have any tricks yet. All we have is we know the antiderivative of elementary functions. We know that by the sum or difference rule, we know that the antiderivative of the sum is same as the antiderivative. You just figure out what is antiderivative of each term, you add it, or same thing for difference, because antiderivative is basically an inverse procedure of taking derivative, right? So inverse of this also works, right? So if you are looking for the antiderivative of f prime, you just need in antiderivative of this. All you need to do is figure out the antiderivative of f and multiply by c, right? So let's try to do our example here. So motivated by our discussion, we just write this as a sum or difference of some elementary function, maybe multiplied by constant. This function here is 0 to 4, 4 times t to 1/2. Try to split it, multiply it. So this minus t to the power 3 over 2 dt, right? Now you can see that this is the difference of two functions. Both functions are polynomial functions, not polynomial, power functions, right? We know the antiderivative derivative of x to a is x to a plus 1 times 1 over a plus 1 if a is different from -1, right? That's one of the results we obtain from the inverse of differentiation, right? So we have a constant. We don't need to worry about constant. So the antiderivative is 4 times none of its power exponent is -1, right? So you get 1 over 1 plus 1/2 times t to the power 1 plus 1/2, then minus 1 over 3 over 2 plus 1 t to the power 3 over 2 plus 1, right? That's the antiderivative. Then you plug in the numbers 4 and 0, right? So all we want to do is just plug in number, right? So this is 4 times, the denominator is 3 over 2, flip it, you get times 2 over 3, you plug in 4, you get 4 to the power 3 over 2 minus, this is the denominator of this term here is 5 over 2, flip it, you get 2 over 5, 4 to the power 5 over 2. Then you plug in 0, which is h over 3, 0 to 3 over 2, minus 2 over 5, 0 to 5 over 2. We know the second group of numbers are zeros. So this is h over 3 times 4 to 3 over 2, minus 2 over 5, 4 to the power 5 over 2, right? So that's basically what we get for this definite integral. And now let's see another example. Example 2 here is integration 0 to 1 and t times 1 plus, no, t plus 1 square dt, right? We are looking for the antiderivative of this function here. Again, here, you can see that this function is a product of two polynomials, and t times t plus 1 square. And we don't have any way to handle product of two functions yet. So our only trick is change the function to sum or difference of elementary functions, or the multiple of constant multiple of elementary function, right? A number time elementary function, sine, cosine, power functions, exponential functions, right? Here we don't have other tricks, just to try to simplify this. This is 0 to 1, t squared plus 2t plus 1 dt. And so this is integration from 0 to 1 t cubed minus 2t squared plus t dt, right? Now after we split it into a sum or difference of these three terms, we can handle term by term, right? So this is t to 4 over 4 plus 2 times t to 3 over 3 plus t squared over 2. Then plug in 0 and plug in 1, make a difference. Plug in 0 for sure, everything is 0, right? And plug in 1, you get 1 over 4 plus 2 over 3 plus 1 over 2. So this is how do we evaluate this definite integral, right? Okay. So let's see another definition here, right? So because this close connection between this definite integral and antiderivative, let's try to introduce a new name for the antiderivative to make the clear connection, right? So we call that, we give a new name for the antiderivative. We call that indefinite integral. So indefinite integral. So this is basically just another name for antiderivative. You can say most general antiderivative derivative. Right, just remove the lower and upper bound. And so the definition for that is the indefinite, we don't have lower and upper bound, f of x dx. So this is equal to capital F of x plus a constant if f prime of x equal to f of x. So this is basically a new notation for antiderivative, right? So from here, we can get lots of rewrite our understanding of antiderivative in terms of indefinite integral, right? So if you have integration, indefinite integral of 1 dx, so this is x plus a constant, and indefinite x to n dx is x to n plus 1 over x over what? Over n plus 1 over n plus 1 plus c. This one has a restriction. N here cannot be -1. Other one, -1, this always work. One more formula, integration 1 over x dx when the exponent is -1. So this is natural log of x plus c, right? This also works for negative numbers, right? When x is negative, this is always true, but you should put a absolute value here. So natural log of absolute value of x. And the what? Indefinite integral of trig functions, sine of x dx, whose derivative is sine. By our discussion before, this is negative cosine of x plus c, whose derivative is cosine of x. By our discussion before, this is sine of x plus c, and integration secant square of x dx is tangent of x dx plus c, plus a constant, and one more very important one, integration e to x dx is e to x plus c, and two more about inverse trig function, integration 1 over 1 plus x squared dx is arctangent of x plus c, integration 1 over 1 over root 1 minus x squared dx is arc psi of x plus c. So that's basically all the antiderivative of all the functions we have here, right? So that's basically yes, the elementary functions we know how to evaluate, right? Okay.